Welcome to Water Supply and Wastewater Engineering class. So today we'll be discussing lecture number 15 and the unit 5, that is water storage tank and the distribution networks. So if you recall, in the last lecture onwards we have started the new unit, that is the distribution network system design. So we have seen different types of layouts which we can lay down before for the distribution of water, and also we have seen the different storage tanks available and how to calculate what is the dimension of storage tanks, how to identify all these things we have discussed in details. So in this lecture we'll be discussing about how to design the water supply plant. So in the last lecture we have seen basically there are four types of different layouts we can choose for the water treatment design, water treatment supply. So first one was dead end approach, if you recall. Then we have discussed about the ring type pattern, and then we have discussed about the radial type, and then we have discussed about the grid type layout. So depending on our requirements, depending on our city type, depending on our how much water has to be delivered, so based on all these different factors we have to choose which type of layout we are using for our water supply design. So once you finalize which type of layout is designed, next one is you have to identify the dimension of pipes, dimension, what is the length of the pipe, all these things you have to quantify. Then only the site engineer will execute the site engineer will construct basically the water pipe networks in across the city. So in this lecture, we'll be focusing on water supply network system design. So we will do pipe network analysis, and then we'll identify how much flow is required, or what is the dimension of pipes, all these things. So pipe network analysis of analysis of water distribution system includes the determination of quantity of flow, means how much flow will be passing through the network. So let me just draw this diagram what we have discussed. So for example, this is your main pipe for which water is coming from the water treatment plant, and that we denote it as a M, right? And from main pipe we have the sub main, so that we distantly denote it as a sub main, which is connected from the main, and again from the sub main we connect it to the household we distribute, that we call it branch B. So these are the three different nomenclature we have seen, and also we use so many valves to restrict the movement of water, right? So in the pipe network analysis, basically what we are doing, basically how much quantity of water will be flowing through each pipe, that we are finding out, and how much will be the total head loss in the various pipe. We have seen in the last class also that there will be head loss once water is passing through these pipes. So how much will be the head loss, all these things we have to quantify it in the pipe network analysis. Then how much will be the water pressure, what will be the dimension of the pipe, all these parameters you have to find it out. So in the pipe network analysis, we have to the in any pipe network, basically the following two conditions must be satisfied. What are these two conditions? The algebraic sum of the pressure drop around the closed loop must be equal to 0. There cannot be no discontinuity in pressure, means how much total pressure, water pressure is there at the inlet, okay, and what are the pressure at the outlet, that this minus this should be equal to what is the loss happened inside the pipe network, right? So there is no discontinuity in the pressure, so that we have to check it. So all the incoming pressure and outgoing pressure, and this includes all the losses also. This is first observation, or the first criteria you have to follow. And next one is the flow entering into the junction must be equal to the flow leaving that junction, that is laws of continuity must be satisfied. Like how much water is coming into the system, so the same quantity of water should go out from the system. So that is the condition, that is the law of continuity. These two conditions has to be satisfied. So first condition is the pressure should be constant, right? Pressure should be equal to sum of the all pressure and incoming pressure, outgoing pressure, and the head loss should be equal to 0. And secondly, the how much quantity of water is coming into the junction, that the same quantity of water should go outside of the junction. It's very simple. So based on these two principles, the pipe networks are generally solved by the method of successive approximation. Basically, we do it. So initially we approximate how much water is going. So how much water is distributed through each pipe, and then we apply the Hardy cross method, and we then again neutralize, or we balance the water flow in each pipe, and then ultimately we get it what is the exact quantity of water is passing through each network, and also how much head loss or the loss of water is happening inside the pipe network. So let's see the Hardy cross method, how exactly it works. So this method is consist of assuming the distribution of flow in an N network. So first we have to assume the distribution of flow, because each pipe initially will, based on our past experience, basically we guess, okay, in this pipe that much quantity of water might be going. So initially we put some random value, or based on our past experience we put some, we assume the distribution of flow in each pipe, okay, such that the principle of continuity is satisfied in the junction. That also we have to take care. And then we take the corrections, because first one we have assumed the distribution of flow, right? But the true case may be different, not maybe the exact thing what we have estimated, or what we have assumed at the beginning. So we have to make the corrections also. So correction of this assumed flow is then computed successively in each pipe loop in the network until the correction is reduced to the acceptable magnitude. Okay. So what you have to do is, once we have the pipe network, initially we assume some quantity of water is flowing in each pipe, and ultimately after that we use this continuity, which is this continuity equations, and we correct our assumptions, and ultimately we get all the parameters. So how the derivation takes place, let's jump into this. So if QA is the assumed flow, so let me draw a pipe network first. So for example, you have a pipe network, something like that. Okay, so water is coming here, so this is inflow, and in every junction water is going out. Maybe this three junction water is going out. So what is happening is, initially water q, maybe for example water is coming here, so q will be distributed in this junction two part, right? Some portion will come here, some portion will come here, depending on the pressure, depending on the dimension of the pipe, the water gets distributed into the two pipes, isn't it? So this is the inflow, and it distributed into two pipe. So how much will be the distribution? Initially what we do, we guess, okay, maybe 50-60% of the water will go in this pipe, that 40% water is going in this pipe. So initially we take the guess, and then we use the Hardy-Court's method, and then we refine our values. So initially we assume that QA is the assumed flow, and capital Q is the actual flow, right? Actual flow will be capital Q, that we don't know at the beginning. We only first assume QA, isn't it? And the correction will be delta, because we assumed QA, or originally it is Q, right? So the correction Q, or the delta, will basically, Q is the actual one minus QA is the assumption. So that division, that subtraction will give you delta, means how much correction is required. So basically Q is equal to QA plus delta. So now the expressing the head loss. So head loss we can express it in this form. HL is the head loss equal to K into, K is the constant, into Q to the power of X. So Q is the quantity of flow, and to the power of X. So this is the normal form of head loss. Okay, so from there you substitute q value already we have done, qa plus delta. So you substitute q value here, qa plus delta. So now if you expanded this expression, if you expand it, you will get, already you have studied in the mathematics course also how to expand this polynomial equations. So you have the qa to the power x plus x qa, that is basically your Taylor series, right? Expansion of Taylor series. So basically how XQA, and this is how we do it. Expansion is happening. So we can ignore the higher order terms, and this is our final term. We can consider first two only. So K into QA to the power X plus X into QA X to the power X minus A into delta. So this is our expression, which is head loss, HL. Okay, so now head loss is already we have computed here. Now around the closed loop, so this is a closed loop, right? The water is going and water is coming out in all four. This is the entire closed loop network. The summation of head loss must be zero, right? That is our principle. Two principles we have seen. One is, how much water is going into this junction. The same quantity of water will go out from the junction. And second one is the summation of all head loss must be equal to zero in the entire system. So the head loss is this one, already we have computed HL. So summation means summation of this entire value should be equal to zero. So okay, so from there basically if we multiply it, summation of k qa to the power x equal to minus, so this entire time you have taken it into the right hand side of the section, and just simplifying this you get this expression. So since delta is same, right? Delta means what? Delta is the correction factor. Correction factor will be same for all the pipes, is not it? For all the pipes correction factor will be same. So You understand now, the delta is a constant, so that's why you can take delta out of summation. So that's why delta came before from the summation, because delta is a constant for all the pipes. Okay, so now delta equal to, simply delta equal to this divided by the entire portion is this one. So basically we have to find out the correction, right? Initially we assume qa, and then we find it out the delta, means correction, isn't it? So based on this correction, again we modify the qa, and then we ultimately get it the q. So the delta already, this is the expression already we have derived it. So since delta is given the same sign, isn't it? So because delta is the minus, uh, this is the entire expression. So now the delta is given as the same sign, right? In the all directions, all pipe in the loop, the denominator of the above expression. So this is the denominator of the above expression is the summation of individual pipe summation, right? So now if you simplify this expression, what you can get is delta is equal to k into qa to the power x, divided by summation of x anyway is there, and this k minus entire term will be there, and l is, that's what we mentioned. So summation of k q to the power, this is, we can denote it as hl. So summation of hl divided by k q to the power x to the power minus a. So basically from here kq, no, hl is what? HL is basically k into q to the power x. So here k into qa to x minus 1 is there, is not it? So if you decompose x minus a is kq to the power x by q to the power a, we can write it, right? Isn't it? So kq to the power x, again it is written as hl divided by q to the power a. So simply if you simplify this expression, you will get this expression. So here is the HL is the head loss for the assumed flow of QA. So once you know the delta is the correction factor. Now you subtract whatever we have assumed at the beginning, and then the entire thing will get modified, all the values, and will get the corrected value. So the numerator in the above expression, means whatever just now we have seen, is the algebraic sum of the head loss in the various pipes of the closed loop computed with the assumed flow. So initially what we do, we assume the flow, and then we find out what is the value of delta, and delta is the correction factor, and then this correction will be distributed across all the pipes, and that's how we achieve our final goal. Since the direction and the magnitude of the flow in a pipe is already assumed, their respective head loss with the due to regard to the sign can be easily calculated after assuming their diameters. So the absolute sum will be this one, already we have find it out, is then calculated. Finally the delta is the correction factor error, basically is the found out in each loop of water, and that's how we do it. So for the value of x, so it will, so we have assumed that k is k into q to the power of x minus 1. So the value of x basically is constant, right? For 1.85 if you use that Hazen-Williams formula, and for 2 if you use Darcy-Weilbart's formula. So this x value, if you are using Hazen-Weilbart's formula, then it is 1.85, but if you use Darcy's flow of water, then you can use x value as 2. Anyway, in this problem we'll be solving one problem in the next few slides. So in that case we'll be using this Hazen-Williams formula. So the x value for our problem will be 1.85. So now let's solve one problem based on the pipe networks. So what is given in the question? So calculate the head loss and the corrected flow in the various pipes of a distribution network system as shown in the figure. So the diameter and the length of the pipe are also given against each pipe. So this is given. Compute the corrected flow after one correction. So only one time you have to run the loop and you have to find it out. So this is the question it's given. So this is a pipe network. If you see the inflow is Q, is 80 liter per second water is coming into the pipe network, and from each pipe, each junction, basically what is going out. And the diameter of each pipe also given to us. D is equal to 30 centimeter, L and length is 500 meter. So this diameter of pipe is 20 centimeter, length is 300 meters. So all these values are given to us. That's not it. So we have to find it out. What is the Q? So 80 is going inside, right? So first let's check how much is going in and how much is going out. So both should be equal to 0, right? As per our principle. So 80 is going in. So how much is going out? So 22, and this 15 also going out. So 15 plus 22 is 37. Again this is going out. So 37 uh, um, plus 24, which comes out to be 61, then you have the 9 going out, 61 plus 9 is 70, and this is again 10 going out, 80. So 80 is going out, 80 is going in, so the continuity is fine here. The flow continuity is good in this network. So this is one we verified, and all the dimension is also given to us. So what you have to find out, compute the corrected flow. So 80 is going inside, right? So now how much of 80 will go this side, how much of 80 will go this side, that we have to find out. That is the question given to us. So it will be divided, right? Half or 50% whatever it is going in this side, and another will be going this side. Similarly, from here it goes this side, and it goes this side, is go this side. So all these things you have to find it out. So that is the question. So first of all, the magnitude as well as the direction of the possible flow in each pipe are assumed by keeping in consideration of law of continuity at each junction. So first we do it where we assume that how much is going this side, how much is going this side. Maybe out of 80, maybe 50 is going in this pipe, for 30 is going in this pipe. Why I assume this 50 is going in this pipe? Because the dimension here, so here pipe dimension is 30 centimeter, whereas this side pipe dimension is 20 centimeter. So this is more wider pipe. That means the flow also will be high, more quantity of water will go in this pipe. So that's why, so initial guess or assumption may be 50 is going here, 30 is going here. So again, from this junction 30 is coming, so 10 is anyway going out, is not it? So remaining 20 will be passing to here and here. Okay, so something like that we have to follow. Continuity you have to follow. So the two closed loops A, B, C, D. So first you can consider it is A, B, C, D. So let me write it here. So this is maybe a one loop you can consider A, B, C, D, and another one is the C, D, E, F. C, D, EF. So this is another loop you can consider. This is the first loop you can consider, and this is the second loop you can consider, and you can find it out using the Hardy-Cross method which we discussed earlier, and we can compute. So yeah, so the solution for this problem will be, so it is given in the question, right? So 80 is coming here, 80 liter per second is coming here, and the each junction, how much quantity of water is going out. So first let's assume that water is going in this section is 45 liter per second, and this is 35 liter per second. So you can assume 40 or any initial guess you can do it. So if your initial guess is wrong, then maybe multiple times you have to do it, the iterations have to do it multiple times. But anyway, you can choose any value at the beginning, starting point. So the assumed flow at AB section, so this is your A, and this is B, C, D, and E, and F, right? So this is the first we have considered this flow, this area. So here AB we have considered it's 45 liter per second. So this is the table we are now considering, the loop at AB, first AB loop we are considering. So the AB pipe, ABCD loop. So this is the ABCD loop. So AB will be plus 43. No, this is not 43 actually, this is 45. Let me correct it here. So this should be 45, right? So this first we considered AB section is the 45 is going, and that is liter per second. Now if you convert it into the meter cube per second, then it will be simply divided by 1000. So this will be meter cube per second. Okay, then dia of pipe is already given to us, which is 30 centimeter. If you convert it into meter, then it will be 0.3 meter, and d to the power of 4.87. So why we got it 4.87 is the constant, right, for our problem, which is nothing but this one. Okay, so d to the power 4. So this is the d value. If you do it to d to the power of 4.87, then this is the value. Right, the length of the pipe is also given to us 500 meter, 500 meter. So now if we are computing K value, so how we are computing the K value? So K value is L by 470 into D to the power of 4.87. From where I got this one? For this, let me do it here. Yeah, so this one, so H head loss HL, already we have computed this expression, right? HL equal to Q to the power of X. So as I mentioned here, we are using this William-Hagen formula. So X value will be 1.85 into L divided by the HL something. If you recall, in the last slide we have derived this expression. So here the values are already substituted. So all these value, if you substitute it, you get K value is L by 470 into X d to the power 4. This one is the expression what we have written it here. So that's how we got this K value. k is a constant value, and we got it this one. So once you substitute all the value, L value is already 500, and d to the power of a 4.87 is this one. So how we got d to the power of 4.87? From this expression, basically we got it. Okay, so this expression we have derived it in the last slide, isn't it? If you recall, just go back and check. Okay, and the x value here we have considered is 1.85, because William-Hagen formula, if you are using that, this will be the x value. So anyway, so k value we computed this one, right? So now once you know the k value, then the compute what is qa. So qa also easily you can compute it. Now hl, head loss, will be k into qa. So k value already computed this one, qa is this one. So q already we assumed, right? 45 to the power of 1.85 will be this value, right? So just substitute all the values in hl, you will get 1.12 is the head loss for the first loop, ab loop. Okay, so the total the head loss, if you substitute all these values what you computed in this expression, you will get this 26. So this is the first expression is over. Now next, for the BC segment, what is the water flow of water we assumed is 23, isn't it? So see how we got 23. See, what we have assumed here is 45, is not it? So 45 water is coming in this junction. Then how much will go here? So here will go, it is given in the question, it is going 22. Then how much remaining will be coming here, isn't it? So 45 it is coming here means what? 45 minus 22 will get 23. So this is a 23 flow is coming here, right? So that's what this is, plus 23. So this direction is we are to considering plus 23. And if you convert it into meter cube per second, if you do it this one, and d value is given to us 20 centimeter, and simply d to the power of 4.87, you will get it this one. And length of the pipe is given to us in the question 300, and all the values you substitute it, you get this line. Now for the CD segment, right? For the CD segment, if you see, and now the 23 is coming here in this segment, right? 23 is coming here, and 15 is going out, is not it? So in this portion also, how much water is coming, that is we consider it is a 20. So how much will be the flow here? So 23 is going into this junction, 15 is coming out of this junction, then again 20 is coming here in this junction. Then how much will be this one? So 23 plus 20 means 43 is going inside the junction. Then output also will be 15 is going out, and 43 minus 15, you will get it is the 28. So 28 will be going downward. So like that, each joint continuity also we have to check it, is not it? Similarly here also, if you see, 35 is going into this junction, is not it? So 10 is going out. So, and this side, 35 is going in, 10 is going out. So now 25 is distributed in this pipe and this pipe. So you assume 20 is going this pipe, 5 is going this pipe. So you can assume some other value also, no problem. Or the corrected value also will be different, and ultimately the final value will get it the same. So this 25, 20 is going here, 5 is going here. So now you know 20 is coming here. So approximately you get all these values, is not it? So for the CD segment also, it is minus 20, because this is opposite side of flow we are considering. So here we are considering flow like that clockwise direction, but here flow is going anti-clockwise direction, is not it? That's why it is minus, and all these values have to duplicate. Similarly for DA section, last part, this is also going anti-clockwise direction flow, that's why minus, and all these value computed. So this is the one. So the net head loss will be this one. If you add all these four values, this is the net head loss, which is 2.53, and this is the net value is 280. And if you add all these things, you will get 281. So now for the loop ABCD, we have delta value. So delta value is already how much? Delta expression is this one, right? Already we have derived it in the last slide, last to last slide. This expression, delta is equal to this expression. Now all the values you just plug in here. So HL is total head loss, right? 2.53, that is there, divided by this entire term for each pipe, is not it? So this is basically 281 is the total, multiplied by the x is what? X into this entire value. So x is how much? 1.85 is the Hagen-Williams formula. X value is 1.85, and this entire term value is we computed is 281. From there you get it is the delta is the correction value, right? So correction value we got it is the 5 liter per second. So whatever we have assumed here, there was error in the assumption, and the correction is 5 liter per second. So we have to rectify all these flows. So AB, what we have considered is actually how much? 45, is not it? So there will be correction for the 5 liter, so it will be 50 actually. Anyway, they have considered 43 accidentally in this, so that's why 5 they have increased 48. But originally it is 45, so 5 you increase it, so it will be 50 here. Now BC, what you have considered is 23, is not it? So 5 has to be corrected, so plus 5 will be 28. Similarly, this one we consider 30. Now it will be plus 5. It is minus 35, right? Minus 35 going anti-clockwise, so it will be plus 5. So it will be minus 30 now. So like that, the correction is taken for the ABCD loop. Now the next table will be for the remaining part, that is the CDEF loop. So for the CDEF loop, the same table you have to make it, and all the same calculation you have to do it, and similarly the corrected values of flow in each pipe has to be computed. So now you understand this AB pipe. So AT is going inside, so AB pipe will be 48 liter per second water is going in the AB pipe, and this AD pipe water is going 30, uh, that is 30 liters per second it is going. So it is not 40, actually it is 50, right? 50 plus 30 will be total 80, how it is distributed. So like that, this is the corrected value. That's what question is asked. So for ABCD loop, we have computed this table. Now next table has to be computed for CDEF, and all these remaining pipes also has to be computed. So this is for the CD DCEF FE pipe, and similar calculation whatever we have done earlier, all this calculation has to be done it. And here also correction factor you got it is minus 7.2. So whatever we have assumed earlier, from there basically 7.2 we have to subtract it, and this is the corrected flow after after considering the corrections. So like that, basically we can design the water distribution system, and this can be implemented so using Hardy cross method. So in this lecture, what we have understood is how to once you finalize the layout, pipe layout. So somewhere, so this is the pipe layout, how pipe is going, so each pipe, how much flow of water is going, what is the pressure, how much is the head loss, all these things we can compute it using the Hardy cross method. And ultimately, we can design, means what will be the dimension of the pipe, what is the length of the pipe, all these parameters we can design it. Once this design is completed, the same layout will be given to the site engineer. So site engineer will construct the exact same dimension of pipe, same location in field, and then in the water system will be designed. So this concludes the first topic, or the first segment of this course, that is water supply and wastewater engineering. So in the water supply, what we have done is starting from collection of water to different, how the water is collected from the source. And the beginning we have seen what are the types of sources available, what are the properties of water, that we have discussed. Then water has been collected from the source and it brought back to the water treatment plant, and inside the water treatment plant we have seen the different steps, are the different units are there. Each unit is purifying some portion of from the water, and some portion of pollutant from the water. And then we have seen how to store the water storage also we have discussed. And then water will be distributed from the storage to the pipe networks, that also we have seen in the last two lectures, how to design the entire water pipe system, right? And how to finalize the dimension, all these things. So this concludes the first segment of this course. Thank you.